Now we'll move on to discussing some linear theory that's going to be necessary for us to be able to understand how to solve nth order linear differential equations. First thing we'll do is we'll discuss what an nth order linear differential equation actually looks like. So nth order and then linear differential equation. So what it looks like is we have some coefficient function a sub n of x, and that's being multiplied by the nth derivative of y with respect to x. And then we'll move regressively, so a sub n minus 1 of x, and then this is being multiplied by 1 less than whatever derivative we started with, so here the n minus 1th derivative, and we move on and on and on, all the way until we get to a sub 1 of x, and it's a subscript 1, so this will be multiplied by the first derivative of y with respect to x, and then plus a sub 0 of x times the 0 derivative of y, which is just known as y. And this is all equal to some function of x. So it's obviously a generalization because we haven't included any specific terms, but all nth order linear differential equations can be written in this form. So one thing that we can learn from this is, well, most of the time when we are solving these differential equations, we're not only going to need the general solution, but we're going to want to find the answer, the solution to an initial value problem, which takes some sort of differential equation like this, and it constrains it, it restricts it to a set of initial conditions. So in this case, we would say, okay, well, we're going to require that y of x sub 0 is equal to y sub 0. And we're also going to require that y prime of x sub 0 is equal to y sub 1. And we're going to require on and on and on until the n minus 1th derivative of x sub 0 is equal to y sub n minus 1. So this is the initial value problem, so IVP, and it's going to say, okay, well, we have this nth order linear differential equation and we have this set of conditions. What is the solution that satisfies both? And so what this might look like, because we do want to put this stuff into practice, what this might look like in practice would be the following. And I'll change colors for that. So an example, we might have, okay, 5 and then y, the fourth derivative of y, and then plus 3 and then times the third derivative of y, which can be written this way. It can also be denoted with 3 primes, so y triple prime, and then plus 2 y double prime, and then maybe plus y prime, and then plus 10y is equal to x squared. And it might say, okay, well, we want the answer to, or the solution of this differential equation. And if we solve this, what we would find is well, y would be equal to some constant times some function. So I will say y1, and then plus some other constant times y2, and then plus some other constant, and then constant times y3, and then plus some other constant times y4, and then on and on. And we have some other terms in there which isn't really necessary to include right now. But in other words, what we would find is if we have a differential equation that is to the 4th power, or of order 4, then we're going to end up having these 4 degrees of variability for constants. And that is why if we have a differential equation that is to the nth power, then we're going to go up to the n minus 1, and then we're also going to have this extra, right? This extra initial condition, which if we have 1 right here, and then we have n minus 1, so we have one condition, and then n minus 1 conditions. If you add those together, then we will have n conditions. So n conditions. And we also see, okay, well, that was an nth order linear differential equation, so we need n conditions. Likewise, we have here a fourth order linear differential equation, which means that we will have 4 degrees of variability, and we will need 4 initial conditions. So we might have y of 0 is equal to 0, and then y prime of 1 is equal, or rather y prime of 0 is equal to 1, and then y double prime of 0 is equal to 2, and then lastly y triple prime of 0 is equal to 3. So these might be our set of initial conditions. Now it would be important to know when we're solving these initial value problems, if the solution that we obtain is actually the only solution that exists. Because we wouldn't necessarily want to find ourselves in a position where we're trying to find the solution of a differential equation, and we find one, but there also exists another one which might be better or might be the correct one to apply in a certain scenario. So it would be important to know when we find the solution to a differential equation whether or not that solution is unique and whether that solution exists. So the theorem that we can use from all of this, so knowing what an nth order linear differential equation looks like and knowing that we're subscribed to some set of initial conditions, then what we can know from all of this is that if, and let me zoom in a little bit more, so if all of our coefficient functions, so a sub n of x, and then a sub n minus 1 of x, and on, all the way down to a sub 1 of x, and a sub 0 of x, and lastly, g of x. So what this would look like in the case of our example, we would have 5, we would have 3, 2, 1, 10, this is a 1 right there, and x squared. If all of those are continuous, so continuous on some interval I, so on an interval I, and I can be any interval that we're choosing. It's often convenient just to choose negative infinity to infinity. If all of them are continuous on that interval I, and a sub n of x, in other words, the leading coefficient or the coefficient of the highest order derivative, in this case that would be 5, and a sub n of x does not equal 0 for all x in I, meaning in the interval that we choose, in this case, if we chose negative infinity to infinity, then a sub n of x could not equal 0 for all x in that interval. And that would certainly be the case here because our a sub n of x, our a sub 4 of x is equal to 5. And under no circumstance, under no input of x from negative infinity to infinity will 5 ever equal 0. It will always equal 5. So if all of our coefficients and our function are continuous on I, and our leading coefficient of the highest order derivative of the differential equation does not equal x in that interval, then the solution to an initial value problem, or the initial value problem, exists and is unique, meaning if we have a linear nth order differential equation like this one right here, and we subscribe it or constrain it to a set of initial conditions, then we can apply this test where we can say, okay, are all of the coefficients and the other function, are they continuous? Well, yeah, they are. They're continuous on the entire real number line. And we also say, okay, well, is the leading coefficient ever 0 on that interval? And no, it's not. Then what that means is when we solve this initial value problem, the solution that we'll find will be a unique solution, meaning there will be no others solutions that satisfy all of those requirements. So that is an important result, and we can rest assured that when we solve these differential equations, we're actually finding the solution that we want.